So optical laser testing, I'm going to discuss 3 different methods today. And again, this is going to be very high level on the different methods. We're not going to go into real detail, but just some things that are out there and things that are beginning to be used in aerospace. I saw kind of the start of this when I was still working at the airline. So I'm going to talk about holography, optical holography, and that's used for finding surface. All of these are primarily used for surface or near surface deformation or damage. And then I'm going to talk about shearography, okay, which is related, again, uses a laser. We got a laser here. We got a laser here under shearography. And then finally, profilometry. Again, it's a laser method. Using sensors and some theory behind the way light works and the particle beam duality, particle wave duality, primarily the wave portion of light. So I'll start with holographic testing. So with holographic testing, we're going to use we're going to map the surface of the part. Okay, and that's kind of all 3 of these are actually going to be doing this. And what we're going to do is with holographic testing, it has to be done in a case where we're going to compare how that surface appears when it's at rest, or when it's just sitting there, and then when it's in a stress condition. And then when that happens is if you have discontinuities, if you have disbonds, these 3 methods are primarily used on composites, by the way. Although laser profilometry, when we get to that, that's used a lot on metal. I'll talk about how we did actually use that on metal. But with holographic testing is when a material reacts to stress. If it's been damaged, or if it's not homogeneous in its structure because of damage, or because of a crack, or because of a disbond, or because of a pocket between layers, that kind of thing, that stress will not be carried evenly through the structure, and so it will cause, when that stress is applied, the deformation that occurs is going to be different in the areas that are good versus the areas that might be damaged. And so we can then measure that. It's very slight. We can use holographic testing to see or to measure where that's happening in order to find that kind of damage, discontinuity, or other items of that nature. So when I talk about stressing it, this is very similar. You'll see a lot of these are similar to there's some play with infrared. With thermography, where we had to excite, we had the excitation techniques. That's one way we can do it. So a part can be stressed. It can be mechanically stressed. And a very common way to mechanically stress something like the fuselage. Anyone have an idea how we might mechanically stress a fuselage of an airplane with everything that's built into the airplane? Yeah. By pressurizing it. You put something under pressure, a pressure vessel, you put pressure inside of it. That's a form of stress you can apply. It can be heat, so kind of like infrared, you can use a heat source. I guess I've got pressure there, which creates a mechanical stress. Vibration, it can be sound-based. Okay, sound is vibration or physical vibration. Or you can do the opposite of pressure. You can put it in a vacuum, and et cetera. And so that'll cause that deformation, and based on the underlying structural condition, the deformation throughout the part is going to vary, and we'll map that using holographic testing. So the theory behind it, and the theory behind a lot of both holography and then when we get to shearography, is that light waves, when they crash into each other, okay, are going to experience interference, okay? So you can get constructive interference where it gets brighter in an area, destructive interference where it gets darker in an area, and it forms an interference pattern. And so if you have two light coming in where the phases, either the phases are different or the frequencies are different, you can get this destructive and constructive interference. And you can start to map that in order to do it. And the way this occurred was a lot of people might be familiar with the Young's double slit experiment, is where it's what proved that light works as both a particle and a wave. And so I'm going to show a quick video on that, actually 2 quick videos on that, and then we'll get into how do we use that property of light in order to perform inspection. So with that constructive and destructive interference, we can then look at those areas to image our surface. And we'll look at how we image the surface here in a sec. But in order to do that, normal photography, light intensity only is recorded. It may be, color photography, it's the intensity of different colors of lights that do it. But holography is we're going to look at the light intensity and the phase. And that phase, whether it's in phase, whether 2 light beams are in phase or out of phase with one another, are going to produce that constructive, destructive, or something in between interference that you saw with the double slit experiments, but just on a much larger scale. So how do we do that? Well, the first thing is, because we're dealing with the phase of light and shifts in it, we have to have light that has a single phase. Normal light that we've got here has all different kinds of phases coming out, right? Different frequencies of lights, which come out as different colors. But with lasers, you have a light that comes out, it's a single color, where essentially the beams, all the waves of light coming out are the same frequency and they're in the same phase. And so what we then can do is, if something causes that phase to shift, we can then see the resulting constructive and destructive interference. And we can use that to kind of essentially create an image of what we're doing, or create a false image, a holographic image of what is going on at a very, very small level. So what we do is the light comes from a laser, and it goes to a split filter, or splitting filter. And that is, it allows some light to pass. It allows some light, it reflects some light at an angle. So in this case, the split filter is at 45, so it's gonna send the light at a 90-degree angle down in this case. But the light that passes, at this point, the light that passes and the light that reflects down still remains in phase. And they're going to stay in phase as they travel, okay? And so then we take that laser beam, and then they go through what they call a spatial filter. It's a fancy name for it. Goes through a lens to spread it out. So it's not just one little narrow beam. We want a little bit wider area. It'd be really slow if all we could image was just the point of a laser beam at a time, right? So we want to spread that out, but the light still at that point is in phase. It's all in phase with each other. We take some of that light and we direct it to our holographic plate. And holographic plates back in the day used to just be like a film. They were basically like a film plate. They were a photoreactive plate made out of a silver type film, or a silver salt photoreactive ion. So that reference beam hits, and that gives us light hitting our plate at the given selected the given selected phase or frequency and phase. The rest of the light, what's known as the object beam, is then directed to whatever object it is we're imaging. And whereas the reference beam has just reflected off of mirrors, which don't change the phase, very, very highly polished, very high quality optic mirrors. The object beam, when light hits any object, it reflects off of it, right? That's what we see. When I see you and I see the building around me, it's the light hitting the wall and reflecting to my eyes. It's the light hitting your clothes and reflecting to my eyes. It's the light hitting the tabletop, and that's what I see, is that reflected light. Okay, the walls are white. They reflect most colors of light. The tabletops are brown, so they reflect greens and reds, but they absorb the blues, right? You don't get the blue that makes up brown, okay? So it's the colors that you don't see that are being absorbed, right? We got Mike's hat over there, bright blue, right? So red, that's absorbing red. It's absorbing green, but it's reflecting the blue back towards me, right? So at the same time, things that are not perfectly smooth or not optically smooth, like a mirror, is going to cause that it's going to cause the light that hits one spot is going to be a little bit behind, that's further away, is going to be a little bit behind the light that might be a little bit closer. And that causes those phases to shift in relation to one another. And more importantly, it causes those phases to shift in relation to the reference beam. And so when those light waves that have now been shifted by reflecting off an object meet up with the original light waves, the reference beam light waves, you're going to get that constructive and destructive interference taking place. And what that'll do, I think I got a little ahead of myself. What that'll do, the beams being out of phase, is they're going to basically create an image on that plate, on that holographic plate, that is light areas and dark areas. Okay, so the light and the dark in this image here is the result of those areas where there's constructive and destructive interference of those different light beams taking place. And so we record that. The holographic plate records that in something that looks like this. Now, to the naked eye, that doesn't look like much. It just maybe looks like a topographic map, right? But that's almost exactly what it is. It is basically a topographic map of the surface of whatever part it is you're doing. And based on the stresses and how that topography forms, we can tell something that may have been smooth before now has different variations to its surface. And so it's that record of an interference pattern. Now what we can do is, if we want to see what it looks like, how many of you have seen a hologram before? Anyone seen a true hologram before? No. So what we can do, and ignore the dinosaur at the right, because we're not using a reflecting plate, we're using a thing. What we can do is we can take our original laser beam, shine it through that topographic looking map. That basically becomes a refracting lens. It's basically like a lens almost. And so if we shine a beam, what's called a reference wave here, that's identical to the original reference beam, so the original wavelength, original phase. If we shine that through that holographic plate and we look at it, it's actually going to create, we'll be able to see a virtual image in there of whatever was used to create that kind of that topographic map looking plate. It works like a diffraction lens. So the hologram acts as a diffraction gradient, which diffracts the laser, which means certain light gets bent towards the eye, other light passes straight, and the light that gets bent towards our eye, the appearance is going to be of whatever object was used to make that holographic plate. Okay. So in this case, this is a virtual image, a viewable one. However, in holographic testing with this, we can, rather than using a plate like that, we can actually use a computerization system. But I guess before we do that, what we'll do is you'll take a holographic plate, a holographic image, with the item that's stressed and with the item not stressed. And what you can do is when you look at that resulting hologram, you can see differences between it. It magnifies differences and makes them visible. Or with a computer, you replace the photographic plate with something called an electronic adder. It's basically a fancy term for a device that can measure that constructive and destructive interference. And then you can analyze the interference patterns that are produced, and you can compare the interference patterns of the non-stressed object with the stressed object, with the same object under stress. And so that can be used then to look at the condition of our part. This is a very, very accurate method. It's very precise. It can find things smaller than a 10,000th of an inch. In fact, it's gone beyond that even nowadays. But it does have some big disadvantages. The first is possible material damage. We're stressing a part. In the process of stressing a part, there's a chance you could overstress the part. Now you go from non-destructive testing to destructive testing. Okay? And that really doesn't do any good. You can tell just by the explanation, the very simplified version of explanation that I'm doing, and the science behind this, that it's a very complex process. People, the individuals who discovered holography and shearography won Nobel Prizes for this stuff. Okay, so it's very, they're writing papers and all that kind of thing when it was discovered. So it's very academic, but it is being put into use practically now. The equipment is very complex and expensive. It has to be kept extremely stable. It can't, because you're measuring such small things and you're using light, you can imagine slight vibrations or movements can throw off that light phasing a little bit. And one thing we do have is differences in object diffusivity, right? How it reflects light can cause problems with this as well and obscure the image. Another method that's been come up with that uses lasers is something called shearography, and this is very closely related to holography, except for the fact that we don't create the hologram. We're not going to use a split beam type system. And so this is another method. Comparison is made between how the surface appears at rest and under stress. So you can see that's the same as holography. The stress methods are the same, okay? But now what happens, again, discontinuities will become visible based on how material deforms when the stress is applied. And it uses that same basic theory, the same basic fact that light acting as a wave is going to have constructive and destructive interference. And what we use is something called laser speckle pattern interferometry. And a long way of saying it. And so now, instead of splitting our beam, okay, we look at how we basically send a coherent monochromatic light, laser again. Now, in this case, it's laser, and they're going to put a lens in front of it to spread it out. Okay, so that's why the beam coming out of the laser is spreading over an area here on the object. We're going to take that monochromatic coherent beam, we're going to spread it out, but you can see we're not splitting the beam in this case. All the light produced by the laser is going to hit the object. Okay? But when it hits the object, the rough surface, the microstructure, even if it appears smooth to the naked eye, that's going to cause some scattering of the light, just like we did with when we were looking at holography, right? The object beam in holography was scattered. It changed the phase. The same thing's going to happen here in shearography. And so now that light that comes off, it's no longer going to be coherent. It's no longer going to be in the same phase. And so we run it through what's called a shearing device, something that kind of separates the phases of light. And we run it into a video camera, and while it's going through that shearing device, phase interference in this case now. So now we still have phase interference taking place, constructive, destructive interference between the waves of light. Is going to, that's going to be taking place where this light coming off here is coming back together into the camera, and it's going to create on individual pixels inside the camera. So it uses a camera now instead of an adder or a plate. The individual pixels in that camera are going to detect whether the intensity is higher or lower based on whether constructive or destructive interference of the light beams is taking place in that specific area. So it's kind of like, we can think of visible light, right? A visible camera, the camera in your cell phone. Visible light hits an object, right? It reflects off that object. It goes to the camera in your cell phone. In that case, your camera is looking at the color, the frequency of the light, and it's looking at the intensity of the light at each pixel. In shearography, the camera, rather than looking at the color and the intensity specifically, it's looking at the lightness, light or dark, based on how those waves are interacting at that given point, and what that phase shift is causing in terms of constructive and destructive interference. And it creates a pattern, a speckle type pattern on our object, okay? Or for our object. So in this case then, that's fed into a computer. The shearographic sensor, which is a fancy name for a fancy camera, is going to feed into a computer, and you can see this also produces, here's our speckled image on this computer shown here. And the software, the imaging algorithm, is going to look at each pixel individually, and it knows what the laser, it knows the intensity and the phase of the light that's being used, that's coming from the laser. And based on that interference and what kind of interference and intensity is being seen on each pixel, it can kind of backtrack to figure out what's happening to that light. If it's traveling a little further, traveling a little bit shorter distance, depending on highs and lows and that kind of thing. And so the images then are taken using that, again, unloaded and loaded, part being stressed. And they are placed one on top of the other. And differences in that pattern, differences in this, and the pattern produced, are able to be picked up to look at how material changes with stress. So if you had a material that reacted, if the entire surface reacted the same under stress and when it's not stressed and then when it's placed under stress, when you put those images on top of each other, they would look the same. They would look identical. But when you have differences in how the material reacts in a given area, that's going to cause differences in that speckle pattern, and that will become evident when you put the two images on top of each other, or when a computer compares them. I do have a link. This link to a video here is a longer discussion about this. If anyone is interested in watching, I just put it in there so you can get it from the slides. So shearographic testing, just like holography, has its advantages and its disadvantages. One advantage, this is very fast. We can do a 1 to 2 meter, and I should say meter square area per second. So 3 feet by 3 feet every second. So you can see it's pretty fast. So it's a large area. It's another very precise measurement. It can do better than 1/10,000th of an inch. Okay. But it has a lot of the same disadvantages. Possible material damage due to stressing of the part. This one has one where surface roughness must be at least one wavelength of light or more in order for this to work. If the surface is so smooth that the differences between different areas are less, the difference in roughness from area to area on a surface is less than the distance of one wavelength of light, you won't get that spec. There won't be enough phase shift taking place that you'll be able to image the object. So it doesn't work for super smooth. And we're talking about polishing down to the micron level here, right? Because these are micrometer waves, very, very small light waves. It's another complex process that requires interpretation and has complex and expensive equipment. It's very specialized. In this one, because we're looking at that light coming together in our, as it comes into that camera, and how the phase shifted beams of light are interacting with one another, you can imagine that outside light, any outside light that gets in, would also interact with those light beams that are coming in. And so it's very sensitive to the lighting conditions, and you need to do it in a dark area where the only real source of light is the shearographic testing equipment. So that's kind of our second laser method. The third laser method we're going to look at is profilometry. And it's also known as 3D optical surface profiling. Of these three, this is the only one I've actually done. I've been part of it. And I wasn't certified in or anything. They were doing it at the hangars I was at. And I kind of was like, oh, that looks interesting. I'll come over and see what's going on. That's the extent of what I've performed with this. But it is really neat, and it did help us. It was a huge step forward, and I'll talk about how that worked. But with profilometry, the part surface is scanned using, again, an optical laser. So we're going to use an optical method. We're going to use a laser. And then we're going to have a camera with either sensors, an array, a CCD, charge coupled device array. But it does use essentially a visible light or a visual type camera to produce a topographical map of the surface. Okay, so this one isn't going to rely on the phase shift so much. We're not relying on the phase shift and the interaction of the different phases of light that are going to the camera. It's going to be more of a standard camera as you know it, you experience it when you're talking about, again, like your cell phone camera or something. And the other thing with profilometry is the part is not stressed during this process. It is simply a passive mapping process. So what it does is we scan an area. We can scan as a point, point, or we can scan in a line, or we can scan a large area at once, depending on how the equipment's set up. And we're going to find things like morphology. Morphology is kind of the shape and contours, right? How the surface morphs from one area to another. We're going to look at, we can measure things like step heights, changes in height, and that kind of thing. And we can look at roughness, how rough or smooth the surface is, as well as other things that we can scan with it. The reflected light in this case now is measured and converted to a distance from the sensor or a distance from a given kind of reference point or a reference plane, okay, which is a function of the sensor. And so we're looking at the light as light hits an object, reflects off that object, goes back to our camera or sensor. We're going to look at the varying intensity as well as the location that it hits on a sensor. And what I mean by that with location is here's an example of a very simple profilometer. So here we have a laser on the left. The light comes down in it. This is showing two different points on a surface. Maybe it has a little bit of roughness, or maybe these are little bumps on the surface. And so what happens is, as the light reflects, it's gonna, it's got an angle coming in. It's gonna come off at the same angle it came in from, right? It's gonna reflect at a given angle, and that's going to hit our sensor in one area, right? That same beam, as part of it, hits a different area, and you can see these have a distance z, a difference of distance of z. That's going to reflect at a slightly different angle, and so it's going to hit a different part of the sensor inside the camera. Okay? And so based on the difference in where those 2 points hit, the delta y that they show there, we can, the camera and the equipment, the processing algorithms in it are able to determine what is the difference in height between these 2 points right here, the two tops of these bumps, okay? Because that light reflecting is going to hit a different part of our camera sensor. Another way to look at it is here is a laser at spread. And so the light comes down, and you can see when it hits different parts of this target, you can see it reflects to different points on this image sensor. And so it can build a three-dimensional model based on where that light is hitting. And so where this was important, where we use this and why this was so important, is it's an extremely fast technique. Look at that. It's very fast. We can do a large area. It's another very precise measurement technique. And it's no contact, no stressing of the part. So it's totally passive. It's kind of like thermography without even needing to do the heating and cooling, right? It's a purely passive thing. And what that allowed us to do is we would take a profilometer, and where it was very critical, where we started to use these a lot, was for hail damage. Because when we'd have an airplane fly through hail, the surface, the top and leading edge of the wings, the nose, the area above the windshield, and the top of the fuselage would look like a golf ball. When you have an airplane that looks like, or when we had 30-something airplanes sitting on the ground in Denver and a massive hailstorm rolled through, and it pelted all our airplanes at once. Every single one of those dents has to be measured. You have to know the diameter of it. You have to know the shape of it. You have to know the depth of it. And you have to map where it is on the airplane and where it is in relation to every other dent. So you can imagine if you have an airplane that's got 1,000 hail dents across it, that's a very lengthy process if you have to get out measurement tools and do each one individually. So where this is being used is we had what planes would come in with an area that had hail damage. Typically the ones that were flying, it was the nose and leading edge of the wings. And the leading edge of the wings were fairly easy to fix. You change out it's expensive, but you can change the leading edges of the wings if you have to. But the nose area was part of the main structure. And so we would use a profilometer to scan the nose of the airplane between the back, the radome and the windshield. That was usually the area that got it the worst. And then what we could do is take that, essentially would create a topographical map of that part of the airplane. We could then take that profilometry data, we could send it to the aircraft manufacturer, to their engineering department. They could put it directly into a computer model, run stress analysis on it and all that, and decide, yes, the plane's good to continue flying, or you need to repair these areas because they're prone to oil canning, or it can fly for 2 months until the next, heavy check. They could make that determination a heck of a lot faster than me having to get out my pen and my measuring tools and kind of outline each dent and measure the size of it and measure the depth of it and figure out how close it is to each piece of structure and each rivet line, and then draw all that data up, draw it all up, and then send it to them. They had raw numbers that could be plugged directly into analysis software. And it was done like taking a picture. It could do small areas like taking a picture. It could scan larger areas, and it wasn't super fast. I mean, when I say fast, it would take 20 minutes to scan this area. But it would take me 20 minutes to do 2 or 3 of the dents, right? So it could do a large area much faster. But it does have some disadvantages. If you have translucent or reflective surfaces, they're difficult to image. Okay, just like if you have heat reflective surfaces, they're difficult to use a thermographic camera to image. It's kind of the same thing. It is sensitive to movement in the environment. That was our biggest problem. We were trying to do this in a hangar, and it didn't take much. Somebody walking up the steps of the airplane would throw it off. I mean, we're talking about thousandth to 10,000th of an inch measurements using a camera. So someone goes and starts to walk, doesn't realize what's going on, starts to walk up the steps, the plane shifts just a little bit in relation to the camera, it's done. You got to start over because you got to reset your reference plane. And the surface has to be clean. Obviously, any dust, dirt, or anything on the surface is going to pick up, anything that's on top of the surface is going to be picked up as that part of the surface being higher or closer to the sensor than a clean area. And so you had to make sure it's clean, which, that's not too bad. Aircraft skin, you wipe it down pretty quick. But, just kind of, so those are the 3 primary types. Profilometry is probably the one that you're most likely to see as you get out into aviation industry. It's the most mature, and like I said, it has the most useful in terms of doing large area damage analysis when you have things like hail being the big one.